Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 3 Part B. So B1 asks us to explain while writing down the energy balance for a flow system. So first I'm going to draw out our flow system. So you just have a container with an inlet and an outlet where there is something going into the system and something going out of the system. For our purposes, we're just going to say that it is full of water. And then our system, I'm going to outline in red right here. So you can clearly see where the inlet and outlet for the systems are. So you have energy coming in, you have energy coming out, and so we want to focus on the energy of the whole system. First, so you have your internal energy plus your kinetic energy, which is V squared over 2, plus potential energy, which is gravity times height, which I'm going to write as Z. And this is all for some unit mass. So next we want to focus on the differential changes of the energy in the system. So we can just add the differential system. And then this change in energy is brought about by the energy that is going into the system and the energy that is going out of the system. So first we can have the energy going into the system, which is the same components as before. You have your internal energy, your kinetic energy, and your potential energy. So that's in per unit mass. And then we're going to subtract the energy going out of the system per unit mass. And then we also want to consider heat, so plus dq, since this is something that can change the amount of energy in a system as well, and any work done on the system. So next we want to focus in on the work for the system. So we want to break that into two parts. So first we have the flow work.
All right, what's your guess?
And this is the work done on the system as well as the work done by the system. So we're going to look at the work done on the system first. And so our work equation is force times distance. So at the inlet, you're going to have a pressure pushing the fluid mass into the system. So we can say that that is our force. So pressure at the inlet. And this is going to be over some volume, which is our distance. So we can do dV at the inlet. Next, we can look at this and see that we have it in terms of volume, while the equation that we were looking at originally is in terms of mass. So we want to be able to switch that over. And so we can relate that by saying that mass is equal to density times volume. And then we can say the differential change in mass in times the density in times the differential volume in. And then we just need to rearrange. So we can say that dV in is equal to dm in over density in. And then we can plug this into the equation that we had right here. And so we can say that pressure at the inlet over the density at the inlet times dV in. And now we need to look at the work done by the system. And so we can use the same logic using the work equation by saying that this time our force is the pressure out, so the pressure at the outlet, over some distance, so dV out this time. And then you would go through the same process as rearranging to get P out over density out times I put V here, but that should definitely be M. So this is dm and dm out, since our goal was to put it in terms of mass in the first place. And the second form of work that we need to consider is the non-flow work. So this is any other type of work that can happen to affect the energy in the system. And so that could be, in this case, since we're saying that we have a fluid, it could be a stir. But if we had a system that contained a gas, it could be the compression of the gas, but it is just another form of work that we need to take into consideration. So now I'm going to plug these into the equation. And to make it a little bit simpler, I'm just going to erase where we had work originally and plug these in. So you have plus P in for density in times dm in. And then you're going to subtract the P out over density out times dm out, since that's the work done by the system, and then our non-flow work. And so now that we've put this in terms of mass, we have two terms that have dm in, and we have two terms that have dm out. So we're just going to combine those terms. So on the left-hand side, we have the change in energy. And then here we have U plus P density plus V squared over 2 plus GZ, and that's in times dm in, and then minus U plus P over density plus V squared over 2 plus GZ out times dm out, and then plus dq plus d. Oops. That doesn't want to work. There we go. dw, and that's the non-flow work. All right, so next we notice that we have these two terms in both our energy coming in and energy coming out portions of the equation. And what we can do with these is recognize that 1 over density is equal to specific volume. And so if we substitute volume in where we see 1 over density, we get internal energy plus P times V. And we know that this is the equation for enthalpy, which is denoted with an H. So we can go ahead and substitute this in, and then we will have our equation for energy balance in a flow system. So I'm just going to write that out, and this is equal to the same thing that's on the left side above. So you have H plus V squared over 2 plus GZ in dm in minus H plus V squared over 2 plus GZ out dm out plus dq plus dw non-flow. Now that we have the energy balance for a flow system, we are ready to move on to B2, which asks us to derive and explain the terms in the Bernoulli equation as it arises from B1. Okay, so if we set up a scenario in which we have, there we go, we have a system that looks like this, where this is in and that is out, which we can call position 1 and 2. And then we are going to say that we are at a steady state for this system. So what that means is that this system is not changing over time. And so when we go back and looked at the equation that we just derived in B1, we see that here on the left-hand side of the equation, we had the differential change in energy. So when we are at this steady state, this is equal to 0. Another thing to note is that down here we have dm in and dm out. And since the mass flow rate in and mass flow rate out are equal, we can just use a common dm when we are looking at our internal energy coming in and our internal energy going out. And so we can write that like this. So you have U2 minus U1 plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1 times dm. And then, of course, we still need to add in our heat. We need to add in our differential work, that's non-flow, as well as our flow energy, our flow work. So we can write that as P2 minus P1 over some common density. Since this again is a steady state, there is not going to be a difference of density at position 1 versus position 2. So next we are going to take a couple of the terms and move them to the left-hand side of the equation and divide the whole thing by dm. And so we will have P1 minus P2 density plus V1 squared minus V2 squared over 2 plus G times Z1 minus Z2 is equal to, now we just have U2 minus U1 plus dq over dm plus dw, which is non-flow work, over dm. And so now what we can look at on the right-hand side of the equation here is this internal energy at position 2 minus internal energy at position 1 plus dq over dm, because this is known as frictional heating. And what this can help us do, if we look at the U2 minus U1 portion, is since there are no phase changes within this steady state, the internal energy is completely associated with temperature change. So we can write that like this. So we have our heat capacity times T2 minus T1. And so this makes it very simple when you have dq dm and dw dm as 0, because you can take a pressure change and find out what your temperature change is, which is very nice, and we have it in a nice simple way here. Now, of course, your dq dm and dw dm are not always 0, but if there are values for that, you can also go and see how these factors change the temperature of your system. But the truly important thing about this equation is the left-hand side right here, because this is what we were looking for. This is the Bernoulli equation when you set your right-hand side equal to 0. So I will rewrite that to make it a little bit more clear exactly what the Bernoulli equation is. This is the potential energy, and this whole thing is set equal to 0. And again, that is what your Bernoulli equation is. Now that we have completed B2, we are ready to move on to B3, which asks us to use B1 to calculate the temperature increase of water arising from flow at constant velocity and potential energy with a pressure drop of 900,000 pascals. So like in the previous problem, we are at a steady state. So again, the rate of mass flow at the inlet and the outlet are going to be equal. So we have dm in is equal to dm out. So we can just use a common dm for that. And then we were given that we are at a constant velocity and a constant potential energy. So that means that our kinetic energy at our initial state and at our final state are equal as well. And then that means that our potential energy at the initial state, the potential energy at the final state are equal. So if we go back to the equation that we derived here, we can see that V1 squared over 2 is being subtracted by V2 squared over 2. And since these are equal values, they will cancel out. And the same goes for the potential energy. We also know that the left-hand side of the equation, which again is written up here, is the differential change in energy of the system. And since we are at a steady state, which means there is no change over time, this is 0. So if we come back over here, we can say that 0 equals enthalpy in minus enthalpy out times dm, and then plus our differential change in heat plus our non-flow work. So in this scenario, we're going to say that this is 0, as there's no heat going into the system and we are not losing any heat, and there is no work, no external work being done on the system. So that leaves us with 0 is equal to the enthalpy in minus the enthalpy out times dm. And if we divide both sides by dm, we have enthalpy in minus enthalpy out. And then if we take one term to the other side, we end up with enthalpy in is equal to enthalpy out. Now from here, what we want to do is break down these enthalpy terms, and we know that the equation for enthalpy is U in plus P in over density is equal to U out plus P out over density. And I'm using a common density since, as we talked about before, at a steady state, your density at your initial state and your final state is the same. And now we can go ahead and get our P over density values on one side of the equation and our internal energy values on one side of the equation. So we will have P in minus P out over density is equal to U out minus U in. So again, we see something very similar to what we saw in a previous problem. So if we go back here, we see that we had this U2 minus U1 is equal to CV times T2 minus T1. Since when there is no phase change, internal energy is completely associated with temperature. So we can write this out. P in minus P out over density is equal to CV times T out minus T in. Now we are ready to start plugging values in. So we know that the drop in pressure is 900,000 pascals. So we can say 9 times 10 to the 5th. And we know that the density of water is 1,000 kilograms per meter cubed. So that is 10 to the 3rd. The heat capacity for water is 4190. And then we are looking for T out. And we're going to say that our initial temperature was 298 kelvins. From there, we can solve for T out. So I'm going to do that very quickly for you guys. So that gives us a final temperature of 298.21 kelvins. And we are looking for the increase, so we can take this value and subtract the temperature in, which is 298, which gives us a temperature increase of 0.21 kelvins. Now we are ready to move on to B4, which asks us to use B2 to calculate the velocity of air rising from a pressure drop of 10,000 pascals. So we can come over here and draw out our system. So we have a container with an outlet of air. Our initial pressure is 10 to the 4th pascals, and our final pressure is 0 pascals. Now we want to use Bernoulli equation to solve for this, and so we can go ahead over here and look at Bernoulli equation. And in this system, there is no change in height, so the potential energy is 0. So when we write this out, we will do P1 minus P2 over density plus V1 squared minus V2 squared over 2 is equal to 0. And we get to use a common density here since there is no significant change in difference in density between the initial and the final positions. So right now we know what our pressure drop is, which is the top part of this term here, but we don't know the density or the velocity. We can calculate the density of air, and then we can go ahead and use that to solve for the velocity. So we know that density is equal to mass over volume, and for a gas, we can do the number of moles times the molecular weight over volume. And we want this in terms of pressure, so we can use the ideal gas law, which is PV equals nRT, to get this N over V value. So this is N over V is equal to P over RT. So we can plug that in to our density equation, and you get pressure times molecular weight over RT. So next what we want to do is calculate the average molecular weight for air, which is mass over the number of moles. And for air, we know that it is 79% nitrogen and 21% oxygen. So when we solve for this, we will do 0.79 times the number of moles times the molar mass for nitrogen, which is 28 grams per mole, plus 0.21 N times 32 grams per mole, all over N. And then we can see that all of these N's will cancel out. And then we get 9 times 28 plus 0.21 times 32. We get approximately 29 grams. So now that we have this, we can approximate that we are at 1 atmosphere and 298 kelvins, and plug that into our density. So now we have 101,325 pascals, and then 29 times 10 to the negative third, since this needs to be in kilograms for all of the units to work out, over 8.314 for R, times 298. So that gets us about, not zero, about 1.2. So now that we have this, we are all set to go back up to our original equation and start plugging in our values. So for our pressure difference, we have 10 to the fourth pascals over the density, which is 1.2, plus V1 squared minus V2 squared over 2 is equal to 0. So the velocity for the initial state is going to be 0, since it is inside of the container. And so we can say that 10 to the fourth over 1.2 is equal to V2 squared over 2, which means that V2 is equal to 2 times 10 to the fourth over 1.2, all under the square root, which gives us 129 meters per second.